University and his PhD at the University of Maryland, College Park, where his focus was on curriculum instruction and instruction in physics. He has done postdoctoral work at both Tufts University and Stanford University. He has collaborated with teams from MIT and the Washington Public School System to design computational modeling curriculum units for use in all science subjects in public high schools, as well as to conduct research on students' learning of science concepts and computational modeling practices. He joined Salem State in 2016, and in addition to being a valued faculty member, he has also coordinated the Collins Observatory since he joined us. His colleague, Dr. Ron Taylor, has mentioned that in his spare time, Dr. Conlin is a talented, upright bass player and can often be heard with his group, the Rum Runners. His talk today is entitled Evolution at the Cosmic Scale. Welcome, Dr. Luke Conlin.
Thank you so much, Dr. Fisher. Thank you all for being here. Thank you to the Department of Biology for putting on this very important festival to celebrate the ideas of Darwin. I think it's needed more than ever. So happy to see all my colleagues and my students and my family here. Yes, I am a bass player. I come from a long line of bass players. My dad is a bass player and his dad was a bass player. So it's an evolution of bass players, maybe? I'm so excited to talk about this topic. It was the subject of my undergraduate honors thesis that I did with Eric Chason, who was the speaker, one of the speakers here in 2019, I think it was. He was going to come here today, but he was a little under the weather. So, all right, going to talk about some of the biggest ideas I know about. Evolution applied to the universe as a whole. Is this a good idea? Or is it a stretch? We'll see. First, you have some homework to do. I want you to show me with your fingers, one or two fingers, how you would fill in the blank for this sentence. Things are getting blank complex over time. One for more, two for less. All right. If you're going to do the one, please use your index finger. Thank you. All right. Check in with your neighbor. Take 30 seconds to explain what you picked and why. It's going to come back later. All right, 10 more seconds to wrap up your conversation. All right, folks, I saw personally from my vantage point a sea of ones with some twos speckled in there in between. There are reasonable reasons for thinking each option, but there is a right answer, which we'll get to. What is a good reason for thinking number one? You sea of ones, there should be somebody among you who could share a good reason for suspecting complexity is increasing over time. Anybody want to share? Yes, the gentleman in front.
The universe is continuing to expand, so it will be harder to put it back into the earlier state, so it's getting more complex instead of less.
Typical bass player answer. Yeah, it would take a lot of work to put the universe back in its box, so that's a good sign it's getting more disordered, more complex over time. I like that. How about a two? Any reason for picking a two? Yes?
I thought about like your phone, there's so much you can do in your pocket with your finger in a wide variety all around the world, like just in your pocket.
Just in your pocket? Yeah, it's saw a meme somewhere along the line. It's like, I could go to bed or I could just access the entire history of the world's information on my phone. Like, well, which one am I going to do? Absolutely, there's complexity in our pocket that is more than we could ever handle in our lifetime. So it definitely feels like things are getting more complex, I would say, but that's a problem. If you went to physics class, you will learn that things are supposed to be becoming more disordered over time, and that's a pretty hard rule. And so we have these intuitions that things are getting more complex, but we have the laws of physics, which say pretty definitively that things must be getting less complex, more disordered over time. How do we resolve those two? So that is the central tension at the center of my remarks today. I'd like to start with what humans are good at. And what humans, I think, are great at is asking questions. Maybe questions are one of my favorite inventions of humankind. We like to ask big questions, and we grapple with them for centuries. Who are we? Why are we here? How did we get here? Where's my car? No, wait, that's not one of them. Are we part of nature, or are we something else? Where did all this something else come from? And did it come from the same place that we did? These are some of the big questions we grapple with for centuries. And we've made progress on a lot of these questions. And one of the biggest leaps of progress in answering some of these questions came from Charles Darwin in 1859. Well, first of all, I will say I'm very nervous. Well, I was very nervous speaking here because, in particular, I'm going to talk about biology. And I know that my esteemed colleagues in biology are so knowledgeable, and I'm sure that I'm going to say some things wrong. But then I realized all my colleagues in biology are so amazing and nice and kind and will teach me for what I get wrong. So correct me. Yes, I have much to learn. So I'm sorry if I say some things wrong, but I'm all ears about learning how to say it more precisely. But my understanding is 1859, Darwin published what some call his dangerous idea that answered some of these big questions. Where does all this complexity come from? Just here we have a few different ecosystems with all sorts of organisms, all very different from each other, but hanging out in the same place in the same time. How did they get here? How do they stay there stably without wiping each other out? Do they help each other? How are these things stable? And where did we humans come from? And did we come from the same kind of processes? Darwin's observations led him to two big ideas that are related to each other. One is that species change over time. And some of these different species that he was seeing at the same time were the result of changes over long periods of time, over many generations. And then the second component of that idea is the how. How did the change happen? And one thing he could not escape but reason his way to is that when there's offspring, there's variation in the offspring. And that variation may fit better with the niche they are living in, or might fit worse. That will affect their chance at survival, which will affect their chance to pass on their variations to the next generation. And therefore, over time, over generations, the later generations will be more adapted to the niche they're living in, if they survive. So that's the idea of survival of the fittest. Here are some finches that Darwin observed on the Galapagos Islands, and you might notice, what do you notice is different about them? What's the same? Sure, yes? Beak shape, okay? We got some big honkers and some pointy ones. That's where I don't have the biological terminology to fill in the blanks there. But we have a wide variety of beak shape. Why? So this is what natural selection helps understand. In observing these birds, they eat different things. Some eat seeds, some eat insects, some use tools to get in between the needles of a cactus and poke insects out of there and eat them. There's all sorts of different ways they eat. So the different beak sizes are going to be better suited for certain kind of eating activities. And eating, I would argue, is important for life. In fact, I think that's one thing physicists and biologists agree on. And so an interesting thing is that natural selection is a different kind of explanation. Some call it an algorithmic explanation. It's so simple, you just follow the steps and the results are inevitable. So that's partly what makes this such a catchy idea and so useful to explain what otherwise would be totally mysterious. Modern biology has made some updates, but they've kept the bones of the theory in place. But some updates include we now know that the hereditary information is encoded in particular molecules, DNA, which Darwin didn't know about. In fact, it might have been predicted by a physicist, which I'll get to. Another tool that biologists have come up with that help explain these things are fitness landscapes. So I just have here a couple of fitness landscapes. Where did my laser pointer go? Maybe I can point with my cursor. Okay, over here we have the finches with a different beak size. Well, beak size is one important parameter that describes how a finch might have an easier time eating or not. Also the shape of the beak, so pointy or blunt. So if we have two parameters to describe the finch beaks, we could plot them on X and Y. So on the X-axis we have the beak size from small to large.
Which button?
Oh, thanks.
Which button, Paul?
Hello? Yes. All right. Can't talk. I'm already talking. There we go. Oh, thank you. All right, yay. So on the x-axis here, on the horizontal axis, we have beak size from small to large. On the vertical axis, we have beak shape from, it looks like, blunt to pointy. And by plotting out all the individuals in a population, you see some patterns emerge. You see, number one, there's kind of two different populations, two different clusters of individuals. And then also you see within those clusters there's variation of beak size and beak shape. And so when there's competition for food, some are going to win and some are going to lose, and that might influence how the beak changes over time. And that's what this graph on the right shows. Same parameters, beak size on the horizontal axis from small to large, and on the vertical axis, beak shape. And if you watch these populations but also encode them by year that they are observed, they drift over time. So here they started, and the beak shape got more snouty, and then it got back to being more pointy. So we get to see dynamics over time by plotting things out this way. So just one innovation that biologists have added on to evolutionary theory to understand it in more detail. Okay, so I mentioned this idea might be considered dangerous, so I want to talk about that a little bit. All ideas might have a certain bit of danger. Oh, my squared got erased there. E equals mc squared is an idea that everybody can recognize the mistake I made there. So, and you're not even physicists, so that's pretty astounding that you could correct my equation in your mind. It's a powerful equation. It tells you that energy and mass are two sides of the same coin. They're interchangeable. If you have mass, that's a form of energy. You can convert it into other forms of energy, like light. And that has certain benefits. We can understand where the sunshine comes from. Hydrogen is moving around so fast in the sun's core, it slams into other hydrogen so fast they stick together and make helium, but some of that mass is missing at the end of the process, and that turns into light, electromagnetic radiation. So it's a powerful idea. It helps us understand things. It also helps us make things. We could, if we're fairly close to figuring out how to do fusion on Earth, that would give cheap energy to the whole world. We wouldn't have to have wars over oil or anything like that. But it also comes with dangers. We could convert that mass into energy and destroy things. So it's not a good or a bad thing, the idea in itself. It is something with trade-offs we have to consider. Same thing with natural selection, some of the benefits. This is from the philosopher Daniel Dennett, who recently passed away, one of the great philosophers of the last 100 years. I had the great pleasure of taking a class with him at Tufts University. Changed my thinking forever. But he has a book called Darwin's Dangerous Idea, which I recommend. And he says that in one stroke, the theory of evolution by natural selection unifies the realm of life, meaning, and purpose with the realm of space and time, cause and effect, mechanism, and physical law. And that is a powerful thing. Helps us understand some of these big mysteries. But on the other hand, it challenges some of our cherished beliefs. And when you challenge cherished beliefs, people will come at you. And so there's a danger to the person having the idea. It's also in danger of being misused. Has been used to justify terrible things and atrocities, and is generally misused when you're trying to argue that one group is superior to another, which the theory does not say. It's not that things are becoming better over time, just more suited to their environment. So there are dangers and benefits, and we should weigh those before we just go around applying this thing to new situations. But I'd say if we're trying to understand the universe, the benefits outweigh the risks. So let's take a look at that. All right. So biologists have asked big questions. Where do we come from? Where does all this stuff come from? Are we the same kind of stuff as this stuff? Did we come from the same processes? And cosmologists have been asking the same questions. Cosmology, by the way, is the study of the universe as a whole. You could think of it as a branch of physics or a branch of astrophysics. We found out when we went to Tufts to visit and to visit the school, decide whether I should go there. My mother discovered that astrophysicists don't appreciate when you call it cosmetology. I don't know, but a lot of my classes make a whole lot more sense now that I'm looking back. I was in the wrong class. Where does all this stuff come from? I want to show you some of this stuff more closely. All right. Up on this top left part of the screen is maybe my favorite picture of all time. I'm not sure, but it's up there. This is the James Webb Space Telescope's deep field image. One of the first times they just pointed at one part of the sky and just stared without blinking for like 48 hours and got all that light to add up so they could see the faintest stuff in the sky. And let's zoom in for a second. Let me point out a couple of things. If you see like a six-sided figure, that's a star in the foreground. It's so bright that it's overexposing the camera. But there's only a couple of those. Everything else is an entire other galaxy with billions and billions of stars of their own right. And now we think every star has at least one planet on average. And so many billions of planets out there in each little dot. There's even crazier stuff. I'll point out right here, see that little smudge that's kind of bent? Einstein, when he came up with his theory of relativity, realized that light, even though it's massless, should be bent by gravity. And so he predicted that we would get some naturally occurring lenses that would help us see deeper into the universe. And that's what's happening there. The foreground galaxy, which is like that yellow blob, is bending the space and time around it so that the light coming from behind, from this distant galaxy, gets smeared out, and we're seeing that process play out. And the lensing part means, even though it's a galaxy at the reaches of our best telescopes, the natural lens boosts the telescope, and we can see individual stars in that galaxy, and we might be able to detect the first stars. We're on the verge of doing that. Over here is also a picture from the James Webb Space Telescope. That is the Eagle Nebula, if I have it correct. And it's big, pillowy clouds of gas and dust. To an astronomer, dust is anything heavier than hydrogen. And there are little, you can see the kind of arms reaching out, and then off the arms you can see little tinier arms. And those are called stellar eggs. Those are new star systems being formed. This is a star-forming region. And when a nearby supernova explodes, it puts pressure on this cloud, which makes it start to collapse into its own star system. And you can see those processes happening in this picture. Down here is an image of the clouds of Jupiter. Yes. And that's from the Juno space probe. And this is from Pluto. This is an image of Pluto from the Next Horizons project. And then this is an astronaut selfie over here. So where does this stuff come from? That's what we want to know. And cosmologists have made progress. We've got some answers too. We have some big picture answers. The main thing that we've learned from studying the universe as a whole is that it is expanding. This graph captures the modern take on the history of the universe. It started a finite amount of time ago. If it didn't start a finite amount of time ago, the night sky would be as bright as the day. The fact that the night sky is dark is only possible because not all of the light has had time to get to us yet. It's only had 13.7 billion years, so there's some stragglers way out there that are still sending their light towards us. Sadly, we might never see it because not only are we expanding, we're accelerating in our expansion. So the light is chasing towards us, but then the universe is spreading out faster than that light can get to us. So, all right, I won't give you the spoiler alert on where the universe is going yet. Big question is, can Darwin's dangerous idea help us to understand our cosmic questions too? And I'm going to point out two specific and very different approaches to extending Darwin's ideas to understand the universe as a whole. Two different ideas. On the left, I color-coded them even because I want to make sure you understand they're two different things. On the left is an approach called cosmic evolution. That's the approach that my former thesis mentor, Eric Chason, talked about back in 2019. It's taking the evolution part and playing that out in a more general sense. And in that story, biological evolution turns out to be one of many epics of a broader cosmic evolution. But it's not necessarily natural selection. It's just evolution as change over time. On the right is a more speculative idea. It's called cosmic natural selection. It is a serious idea, but it's speculative. It's one of my favorite ideas, which is why I have to talk about it. But it's, spoiler alert, probably not true. But very fun to think about and very powerful for approaching problems in a new way. So first I'll talk about cosmic evolution. This is the idea that evolution, writ large, means change over time. And so that's one of Darwin's observations of the species. They change over time. And so what if we think broader than species? What if we think about the universe as a whole? Things are changing over time. And they change over time in a very interesting way when you look at it this way. Like my dad said, the universe is expanding. It's hard to get it back. Same thing with a gas cloud. When you puff a little spray of perfume, eventually it will fill the room and people over there will be able to smell it. It never gathers itself back into the bottle. Same thing for the universe. It's expanding, and as it expands, much like a gas cloud, it goes through phase changes. As it cools down, gas might turn into a liquid and then a solid if it gets cold enough. The universe turns into people. Harlow Shapley, one of the great astronomers of the 1800s, said hydrogen is a mostly inert gas that, given enough time, turns into people. So I'm going to tell you a couple of different points along the way. But sorry to throw, this is I think the second of two equations that I'll put at you. This is the second law of thermodynamics. Closed systems have no choice but to either increase their entropy or at best stay constant entropy. They can never decrease their entropy. What is entropy? Entropy is, you'll hear it described as a measure of disorder of a system. And that's good enough to stay in your mind. It's not precise in a physicist sort of way. It's more about how the energy in a system is distributed. If it's all concentrated in one spot, you can use that energy. If it's spread out amongst the whole system, you can't use it anymore. So that's why heat transfers from hot objects to cold objects. It doesn't go the other way around, unless you plug in your refrigerator. But then it's not a closed system anymore. So it only applies to closed systems. When nothing can come in or out, no energy or matter can come in or out, then entropy has to increase or at best stay constant. And so that's why you spray some perfume, it will spread out, but you can never get it back into the bottle. Sir Eddington, who was one of the ones that proved Einstein's theory of gravity right, but with an observation of the solar eclipse of 1919, said that the law of entropy, always increasing, holds, I think, supreme position among the laws of nature. If your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. That's cold, that's cold. And that's what I think whenever YouTube pops up an advertisement for, they have these heaters that you can plug into the wall and will heat any room without wasting any heat. And I'm like, oh, Sir Eddington would be very upset about this. Okay. We all have the intuition that complexity is increasing over time. We can't be wrong about that. I mean, our cell phones are more complex than a hydrogen atom, I would guess, because it's got hydrogen atoms in there and it's got, they're interacting with other parts. So complexity must be increasing over time, but complexity is the opposite of entropy. So we have an apparent paradox. How can things be increasing over time? How can complexity be increasing over time? The idea comes back to closed systems. The universe is a closed system, maybe the closed system. And so entropy has no choice but to increase. But on local levels, you have little pockets of energy that are moving from one thing to another. And those energy flows are where the interesting stuff can happen. So life is one example of this, where we are able to separate ourselves from the entropy we can't help but create. In other words, we decrease entropy locally in our bodies and in our systems, but we make a lot more heat and waste in the universe as a result. And the entropy that we increase the universe by far outweighs the decrease that we are able to manage to hold on to for a little while locally. Okay, so one other interesting aspect that I love about this idea is that if you follow the Big Bang to the present time and keep going, it's not just that the universe goes through phase changes, it's that each phase change makes a new structure and that becomes the stage for the next epoch of evolution. So at the Big Bang, or right after the Big Bang, we have the universe started in a hot and dense state. It was so hot that by E equals mc squared, the energy of radiation floating around was the same energy as our most massive particles, like protons and neutrons. And so they can emerge just by E equals mc squared from energy to mass. If it's the right energy, it'll turn into mass. So at first we started with particles. And they were moving around so fast that they couldn't hang out together. They were just zipping around. And the universe was opaque because any light that was going through it would bounce off the particles. But then after about 300,000 years, it was cool enough, it's expanded and cooled to the point where atoms could form. Electrons would get close enough to protons and form hydrogen. And hydrogen was about as complex as it could get. It's too hot for anything else. A little bit of helium, that was it at the start of the universe. Well, hydrogen and helium is all you need to make galaxies and maybe some dark matter. And then as you're making galaxies, it can collapse further into stars. And then the stars fuse hydrogen into helium, and you get more helium. And then they run out of fuel and they collapse. But then that makes them hot enough to burn helium into carbon. And then they run out of fuel and they collapse. And then that makes them hot enough to make oxygen, and like about half of the heavier elements come from stars. And that's why we are star stuff. We are made in the cores of stars. The atoms that make us came from stars and then exploded and then made other stars start forming when they hit their gas cloud and so on and so forth. So stellar evolution. Once you have the heavier elements, then you can have planets. So the first generation of stars did not have planets, but after that we had heavier elements that can make planets. Now we think every star pretty much has at least one planet on average. Once you have planets, you have chemistry. Chemistry can happen in space too, but planets are really good for making chemistry happen. You have a lot of energy flowing, so the chemistry can get interesting. All right, I have, on my way here, I put a bunch of paper clips in my pocket, because if you get enough paper clips together, you ever notice they always end up connected to each other? No matter, you can't get them, especially when you need them. That's what happened to the chemical environment on early Earth. If you have complex enough chemistry, the pathways get tangled, and you get autocatalytic reactions, where the reactions make the things that make the reactions easier to make. So it's a self-perpetuating phenomenon. So that comes from the idea put out by Stuart Kauffman, biologist, in the book At Home in the Universe, which I highly recommend. So chemistry has its own evolution that might lead to biological evolution, and then that might lead to cultural evolution, and who knows where we're going to take it from there. How do we make sense of the fact that complexity is arising locally, but globally it's becoming more disordered? One way of looking at it is by looking at the energy flows. This is just a way of putting a number on it. The energy rate density. So energy divided by time, that's the rate, and then also divided by mass, so how dense it is. And if you follow that number, it increases for each epoch of evolution. Galaxies have a lower energy rate density than stars, which have a lower energy density than planets and animals and societies. So this is from Eric Chasson's book, Cosmic Evolution, which I highly recommend. So, to put it all in a nutshell, cosmic evolution tells the big history of how energy flows allow complexity to grow locally, but globally, the second law of thermodynamics is still playing out. The universe is becoming more disordered at the grandest scales. All right. How does that sit with people? You feel better now? Are you going to be able to sleep tonight? Okay. All right. Okay. All right, pop quiz. Same question. What's your thoughts now? Things are getting blank complex over time. Right? I want to see ones and twos. What are you feeling now that we've talked about a little bit? 5. There's good reasons to suspect 5, but it's hard to prove. All right, cool. I feel like there should be a third option. Mostly a physicist's answer would be it's definitely getting less complex at the broadest scale, but more complex locally. So it's kind of both, but really less at the biggest scales. All right, let's go on to the second idea. All right, that's all well and good, but what about the natural selection part? Wouldn't it be interesting to apply that to the whole universe. So, it's going to get a little crazy. The craziest thing that really bothers physicists is not only how did life arise, but how do we even find ourselves in a universe that is hospitable for life? If you think about the fundamental physics here, there's the laws of physics, Newton's laws, you could say, or conservation of energy, but then there's the stuff, the particles, the electrons, the protons. You could still have the same laws of physics, but have an electron have a different mass, or a proton have a different mass. And what would that universe be like? You can play this out. These are what are called free parameters in the theory. You could change the mass of the electron, the theory still holds, but you might have a different kind of universe. When you think of it that way, varying the mass of an electron, even in the 12th decimal point, might make life impossible in that hypothetical universe. Here's a graph that shows the electron mass on the horizontal axis, and then neutron mass on the vertical axis. So the neutron is 1,800 times the mass of the electron, so we can't even make that point here for the electron. And then, if the neutron was, instead of 1,800 times the mass of the electron, let's say it was 1,803 times the mass of the electron, at that point you would no longer be able to have stable nuclei. And therefore, no stars, no life. So, just the tiniest tweak of any of the properties of the universe, constituents, would make the universe inhospitable for life. So that just really hammers home the fact that it's an amazing coincidence that we live in a universe that has the possibility of life. Physicists don't like coincidences. If it seems like a really big coincidence, it's a thing to explain. And so it would be really nice if we could. And I'm going to give you an explanation for this that's going to work pretty well. The problem is, first we have to solve another mystery, which is what's inside of a black hole. Oh, man. How many people here have heard of a black hole before? All right, almost everybody. How many people feel like they have an understanding of what the heck a black hole is? All right, intellectually humble group, I respect that. A black hole is a point of no return from our universe. In Einstein's theory of gravity, space and time is like a fabric that dips in the presence of energy or mass. So in this case, the Earth makes a dip. So satellites, if they're going fast enough around, they will go in orbits around. So this is the theory of gravity. In those kind of terms, a black hole is something so dense that the dip is so steep nothing can get out, not even the fastest thing in the universe, which is light. And that's why black holes are black, because we can't get light from them. So that's the idea. Okay, an analogy is like a whirlpool that's so steep no boat on Earth could get out of it. There's a point of no return called the event horizon. Here's the anatomy of a black hole in how we usually find them in our universe. Things are usually falling into them. And on their way down, they flatten out into a pancake, and they're all bumping into each other, so they get really hot. And then sometimes they kick out some charged particles, which get ripped away into these jets that go almost the speed of light away from the black hole. So it's not that they're coming from the black part of the black hole. It's like they just escaped falling into the black hole, but they got sent off somewhere else. But then once you pass the event horizon, there's no coming back. And there's no telling anybody how things are going in there. Which is why it's so hard to know what's going on in there. All right. Here is the galaxy M87, and we noticed a long time ago there's this weird straight line in there coming out from the galaxy. And a long time ago, astronomers were like, well, that's weird. And what is it, the movie? They said, God doesn't build in straight lines. But there's a straight line. You don't find straight lines very often in astronomy. So they wondered what this is. Turns out it's the jet part of the supermassive black hole that's in the center of this galaxy. The first image of the black hole the first image of a black part of a black hole that we ever got was this one right here. It made all the covers of the newspapers a few years back. That is the black hole in the center of that galaxy, M87. And our whole solar system, including Pluto, if you include Pluto, which I do in my heart anyway, we would all be in the black part of the black hole. This thing is way bigger than our solar system, twice its size. How do black holes form in our universe? Either from stars at the end of their life, if they're massive enough, they explode in a supernova, one of the most powerful things in our universe, and the core gets collapsed down into something so dense that it turns into a black hole. And its gravity is so strong, light cannot escape. Galactic black holes. I just showed you M87 galaxy and the supermassive black hole at the center of that. We're not sure how those start. Maybe they start with stellar black holes and then accumulate, or maybe they're primordial black holes, a region of space-time that had so much energy right off the bat after the Big Bang that it just turned into a black hole immediately because of quantum fluctuations or something like that. So we're not 100% sure on that one. So it depends on the details how that happened. All right, what's inside of a black hole? The short answer is nobody knows, and it's impossible to find out. But if we try anyway, we can make some progress. We know that things falling in will get squished to extremely high density. Hey, what's the equation for density? All right, I have some students here. They should be able to...
Density is equal to mass divided by volume.
Mass over volume. Excellent. 100 points. I read my mind, too. Density is mass over volume. Well, wait a minute. What happens if mass is constant, or even really big, and then volume goes to 0 at the central point of the black hole? Uh-oh. You're not allowed to do that in math class. They'll send you the principal's office if you try and divide by 0. That is called a singularity. The theory blows up. We can't trust the theory anymore as it is. So we know, that's one great thing about physicists. They have rules, but they also tell you when not to apply them. And so don't apply our rules to the singularity. That's when we know we don't know. But let's try it anyway. All right. There are some ideas about what might happen there. You have to combine the theory of gravity with the theory of particles. The smallest stuff in the universe, quantum field theory, and the biggest stuff in the universe, gravitationally bound objects. We can't do that. It's the holy grail of physics. Nobody knows how to do it. But we can try anyway. All right. One hypothesis for what happens when you combine general relativity with quantum field theory is that the quantum fluctuations don't allow the singularity to happen. Before it gets down to one point, it has to spread out a little bit. And if it spreads out a little bit, maybe it keeps inflating like a balloon. And so instead of going down to a single point, space-time will kind of pinch off into a whole new bubble. Well, that sounds an awful lot like the Big Bang, doesn't it? And so one person's black hole could be a whole new universe's Big Bang. We could be in a black hole right now. It would explain a couple of things anyway. Here we are in this universe, but that universe is in like an offspring of another universe where a black hole formed. All right. Oh, man. It's getting to be the multiverse of madness here. Every single black hole makes a whole new universe. That new universe might have black holes forming in it, and that would make new universes, and then new universes all the way down. If you study enough particle physics and Big Bang cosmology, you might start to convince yourself it has to be this way, because if the universe is infinite in extent, you still can't escape it, because there's going to be regions of space-time that are so big that anything that is possible will happen somewhere in that great cosmos. And so the laws of physics might change in distant regions of space-time that we don't know about. So this idea is plausible, even if it's a little crazy. So here we get back to natural selection. Each universe that forms from a black hole could have slightly different parameters. Maybe the mass of the electron is slightly different in the offspring universe, or maybe the mass of the proton is. Well, a lot of those universes will not be able to form stars or life, because the mass of the electron changed too much. And so you'll have a lot of universes that just peter off. They don't have offspring. They do not survive. On the other hand, you'll have some that make a black hole, and then those are going to make offspring which are kind of close to the original, so they have a bigger chance of making black holes. They're tweaking the parameters a little bit, but you're still in the right neighborhood. And so this is where the fitness landscape can help cosmologists. Here is a fitness landscape for the multiverse. Here's on the x-axis, we could call it the electron mass, from small to large. Here's the difference between the proton and neutron mass, which is a few electrons worth of mass. It doesn't really matter, just any two parameters, x and y. And then the vertical axis is how many black holes that universe produces. You might start off over here. You might make only one black hole in your universe. But you were in the right neighborhood anyway, so that black hole in your universe will make another black hole. And then that was in the right neighborhood, so its offspring might make two black holes. And then eventually you're going to find yourself in a universe that is going to have a lot of black holes. Okay. So biological evolution by natural selection, the variation leads to adaptations that make an organism more fit for its niche. Cosmic natural selection seems to select for more black holes, which is weird. But we're lucky, because if you have more black holes, that means you also have more stars and more planets and more possibilities for life. So we're just coming along for the ride. It's really all about the black holes, but life is a pleasant byproduct. I think it's pleasant. Yes, it's pleasant. Okay. Is this just speculation? Kind of, yes. But it's not just speculation. It is speculative. It's probably not right. But we can let the world tell us if it's right or not. It is science. And so this theory does make predictions that are testable. One kind of prediction is that has to do with the threshold of how dense a star has to be in order to form a black hole. So the cutoff is like 3 solar masses, and our universe has about that threshold. So we're right on the cusp of this thing being supported by some evidence. So I wouldn't bet the house on this one, but it is worth considering because of the benefits. What's the benefit? It explains one of the hardest questions we've ever asked, which is, why do we find ourselves in a universe that could support life? So, bringing it back to our two approaches, each one has its benefit. Cosmic evolution expands the idea of evolution to think about change over time in the universe. And we can resolve the idea that complexity arises locally while still making entropy increase globally. That's probably true. Cosmic evolution as an account is not really any new science. It's a synthesis of the established science that we already have. So that one I would bet the house on. Cosmic natural selection, that is a fascinating idea that solves some of our biggest problems, but there's so many what-ifs in there that we can't really bet on it yet because we don't know what really goes on inside a black hole. But it is at least grounded in theory that is plausible and makes observational predictions. So the jury's still out on that one. So we've addressed some of the biggest questions humans have ever asked, and I feel very grateful for the privilege of being able to do that and to share this with you. Thank you for being here and thinking through this. It is extremely important that we can do this, that we can share our thinking and our ideas, and we need the space to ask the big questions, and they might be dangerous. So we should never forget to weigh the benefits and the risks of doing so. Thank you so much to the Department of Biology for hosting me, and thank you to my Chemistry and Physics Department for sponsoring me and for all the amazing intellectual conversations, and special thanks to my wife for creating a little pocket of order amidst all the disorder so that I can actually write this talk. And keep asking questions. And so now I'm going to turn it to the questions part. Thank you. Thank you. Dark matter is something that we don't know what it is, but we are pretty sure it is much more common than the regular neutrons and protons and electrons that we're familiar with. Most of the matter that we are aware of makes up only approximately 4% of the entire makeup of the energy of the universe. Most of it is dark energy, which is another thing we're not sure about. And dark matter is, we know it's there because of its gravitational effect. So it's definitely having an effect. And it's acting as if, it's acting with the same kind of gravity that the matter we know about acts with. It's, there's no new gravity. And we see it in galaxies. Vera Rubin, the astronomer, was the first to detect it in the rotation curves of galaxies. Galaxies spin, and based on Newton's law of gravity, as you go further out, like it drops off as 1 over r squared, so it should go slower and slower as you go out. But Vera Rubin found that it stays constant, and that was the first sign that something is there that we're not seeing, but we can detect its gravitational effect. It's also making galaxy clusters move faster than they otherwise would have. We can detect the gravitational effect of galaxies holding together. And so we know from various lines of evidence that it's definitely there. There are 2 main theories of what it could be. Acronyms are machos and WIMPs. It's kind of they got a little too creative there. But machos is massive particles, like maybe they're Jupiters, maybe they're black holes, maybe they're things that are regular old matter we know how to think about, but we just can't see them observationally. The other possibility is WIMPs, which is weakly interacting massive particles, which are things that do not interact with the electromagnetic force. So there's no light, literally no light coming from them, which is why they're dark. And there would have to be a new kind of thing that we don't know about yet. There's leading theories and that sort of thing. We know enough to be pretty sure that it is a new kind of thing. The WIMPs are winning. But we don't know what that thing is yet. But we know there's a lot more of it than what we got. And it might be what, it comes down to the question of, on this graph, I put galaxies, well, Eric Chason put galaxies first and then stars. What came first, stars or galaxies? Some people would be like, how could you have a galaxy without a star? But dark matter might have been the thing that made galaxies come together first, and then stars started populating the galaxies. So, sure, yes, Paul. Oh, Dan.
Yeah, most galaxies have a black hole at the center, or do all of them have a black hole at the center?
I haven't checked them all, but most of them, yes. We now think that almost all the galaxies have a supermassive black hole at the center.
But how would you detect a black hole that wasn't at the center of the galaxy?
How would you detect a galaxy that doesn't have a black hole there? Or like,
Other way around.
or,
How do you detect a black hole that doesn't have a galaxy?
oh, so a black hole that doesn't have a galaxy?
Yeah.
It would be hard because they go silent. We detect them when they're eating. And the one that I showed, M87, we looked a year later and it looked different, like it changes over time. But it's because it's eating. So if it happens to get expelled from its galaxy, or if it never got a galaxy to hang out with it, then we would have a hard time detecting it. So that could be a component of dark matter, is black holes that are out and about in the universe without that they're not eating currently, so we don't see them. Hi, Paul.
Thanks
Yeah.
for the thought.
Thank you.
In common usage, the word universe means everything that exists.
Yeah. Oh man.
What does the word mean when a cosmologist says universe?
All the everythings that exist. You broke my brain. I can't answer you. I don't know. I will say that maybe a universe in that context is used to say a region of space-time that obeys the same set of rules and has the same set of parameters of electron masses and proton masses and all the itty-bitties.
I have another question over
Yes.
here.
So I was wondering, why are entropy and complexity opposites? Because wouldn't something more random, like, be more difficult to figure out? Like, how do you define complexity?
Yes, that's a great question. And it's a tough question, but
When you say complexity, are you referring to organization?
yes, I'm using it somewhat synonymously with organization. There are different words that people use in the same field. Self-organization is a thing amongst complex systems scientists. Information is often used as kind of the opposite of entropy. It's called let's see. There's a microscopic definition of entropy, which is all the different microstates that make up the system. It's the number of those. That's it. The log of the number of the different ways you could arrange things to have the same macroscopic properties like pressure and volume and that sort of thing. So there's a macroscopic way of defining it, but also a microscopic way. The information is the inverse of that. So I think of inverse of entropy is information. How many bits would you need to describe the system completely? That's Shannon information. And so there's kind of this growing consensus among physicists that information might be like the common currency of the universe, not energy. You can find violations of the conservation of energy if you look hard enough, but you can't find violations of the idea that information cannot be destroyed. And the battlegrounds are actually on the event horizons of black holes. What happens to information that falls into a black hole? Does it get stored on the surface, or does it get destroyed? Do we ever get it back when the black holes evaporate by Hawking radiation? That's the forefront of black hole physics, is what happens to information. So information is how I think of the opposite of entropy. Complexity is, I'm using it synonymous with information, I'd say. So it's the inverse of entropy. But I agree with you that if it's more complex, it would be harder to describe. If it's all spread out, it would be hard to count up all that stuff. But that's not the sort of thing I'm talking about. It's, yeah, organization is closer to what I'm talking about. Yeah.
Do you have any other questions?
If the theory that like, if the theory that like each black hole has like a new universe, when two black holes merge, like would we have that assumed universe or two different coexisting?
You just blew my mind. Thank you. That's like a question I never thought about before. That's great. I do know there is, certain physicists are worried about, what's the term? I just want to get the term right in my mind. All right, so Alex Vilenkin is the world's preeminent scholar of nothing. He's at Tufts University in the cosmology group. Let's see, Alex Vilenkin. Nothing in physics is not what you expect it to be. There's no such thing as nothing. There's always particles coming into and out of existence. And so there's always a baseline amount of energy, even if you like clear out all the stuff from a little pocket of space. There's still energy there and stuff there that will just pop into existence anyway. That energy level might be the ground state, or there might be a lower one down. And if there's a transition where it breaks that symmetry all of a sudden and goes to a lower state, that will expand outwards and destroy everything in its path. And so some physicists are worried about this happening in our universe, and so my intuition is that that's the sort of thing that might happen if two black holes, which are really their own universes, collide in our universe. My guess is it'd be like the movie Never-Ending Story. The nothing will sweep through and like destroy everything in both universes. But maybe if we write that up, we can get a paper published on that. That's a great question. Thank you.
So it was a fantastic talk.
Thank you.
Thank you very much. So I have a simple question. So in the beginning, there is an equal chance of having matter and the antimatter. So we know we have anti-electrons, anti-neutrons, anti-protons, anti-everything. But where does the antimatter?
I love that question, and so the question is, when in the early universe I said like particles pop into existence, if it's the right energy of the radiation that's there, it will become mass and become an electron if it's that energy. The problem is you can't just create an electron because that's a negative particle. The conservation of charge says you can't create charge or destroy it. You can only move it around. Well, that's not exactly true. You can create it as long as you create equal amounts of the opposite charge. So electrons can pop into existence, but only if anti-electrons also pop into existence, which have the same mass, same energy, but opposite electric charge. And you can't do one without the other. So every time an electron is created, there should be an anti-electron, also called a positron. So if that's true, where is all the antimatter is the question, which is the biggest, one of the biggest unsolved mysteries in all of physics. And so I don't have an answer for you, but if somebody does, they might win the Nobel Prize. There are some ideas about where all the antimatter is. I personally made my own bumper sticker. Where's all the antimatter? And I had that on my car for a while. So I'm still looking. But there might have been just a slight imbalance in some laws of physics that we haven't quite worked out yet. There is some symmetry that is broken that one of America's great physicists, experimental physicists, found an asymmetry in the weak force that might help explain. There's just like a slight imbalance in matter and antimatter, and so they all annihilated each other, and then whatever was more of, that's what we have now. And so I guess that's matter. Matter wins. Okay. Yes. Yes.
That picture of was it M80 or
M87? Yeah.
M87. Just curious, how long ago did that actually happen? What happened in that picture, and what's it likely up to now?
See if I can find it. There we go. M87. M87 is, that is a good time to plug our telescope on the roof. You can see M87 using the Collins Observatory on the roof of Meyer Hall. So come on up on Monday nights, 7 to 10 p.m., as long as it's not a school holiday, and as long as it's not cloudy, and as long as the telescope is not broken, we will be able to see M87. So it's, I don't remember exactly, but it's, let's see, hundreds of millions of light years away. So our Milky Way galaxy is about 500,000 light years across. The nearest big galaxy is Andromeda, which is 2 million light years away. This is like 100 times that distance away. But it's actually an absolutely ginormous, technical term, galaxy. So it's so big that even though it's so far away, that supermassive black hole was our best shot of seeing the black part of a black hole, because the massive, how huge that black hole is, even though it's far away. So this is 100 million years ago that we're looking at it. And what has happened in the meantime is it's probably eaten more stars, and it's an elliptical galaxy, which means it probably collided with another spiral galaxy in the past, and then it all got glommed together. And maybe the supermassive black holes of each galaxy combined into a bigger one. And so I think in the meantime it's been eating, but I don't know for sure. They haven't called me back. Yes, hi.
Hi, thank you so much for this fascinating talk. I'm embarrassed to say I have so many questions that
That's great.
Come to my mind. I might just ask them, and then feel free to ignore the ones that you don't feel like answering.
That's nice.
This was a clarification question about information and entropy. I would think that as entropy increases, you need more information to describe it. Whereas when there's less entropy, it might be a symmetry, which could be explained more quickly. So maybe I'm understanding that incorrectly, but some clarification on sort of thinking about those things. And then the other question is about this idea that a black hole, like spawns another universe. It troubles to me this idea that then a universe is a closed system, because isn't there energy coming in through that black hole? So by definition, it's not a closed system. So I don't know if we have an understanding of that. And then third, do you have any predictions about the shape that a universe would take from a singularity? Or do we think it would be flat? Do we think it would be round? Are there any predictions? And then finally, in the cosmic evolution diagram you had, it sort of looked like progress was like getting to humans, and we're this pinnacle. Do you think there are any negative ramifications in your field of thinking anthropocentrically? Do you see evidence that we do think quite anthropocentrically? And if so, what are tweaks to that way of thinking that can make us a bit more all-encompassing? Yeah, thank you.
Those questions are amazing. Two of them are questions that I decided if I got asked, I might run out of the room. So bye-bye. All right. Great question. So let me recap. Number one is information and entropy. Little clarification on that, because it seems like if it's more spread out, it would take more information to describe it. That's a great question. Number two was if you have any... Oh, yeah, I had this thought on the way here. These two pictures that I painted are at odds with each other because of that. Because I said entropy has to be increasing in our account of the universe because it's a closed system. But down on the right, I'm saying it's not closed. So you are right to question that. So maybe the all holds are maybe entropy can decrease in some of these universes, which would be interesting. The third one was, what is the shape, any predictions for the shape of the universe after Big Bang? First, a little bit about shape in 4 dimensions. It's a little trickier to talk about, but flat in 4 dimensions means if I draw a triangle, it'll have 180 degrees inside. All the angles add up to 180 degrees. If I draw a triangle on a globe, like if I'm a little ant at the North Pole and I walk to the equator, and then I take a right-hand turn, walk along the equator for half the globe, and then take another right, I can make a triangle with 270 degrees, 90, 90, 90, 3 90-degree turns. So that's what curvature means, is like, does geometry work in the way that we expect, or does it work in according to different rules? The cosmologists for our universe found that it was extraordinarily flat, which is weird, because if there's any little tweak away from flatness, it should amplify almost immediately. So the fact that we're so close to flat is one of the mysteries of the universe that is solved by this word inflation. The idea that right after the Big Bang, it banged faster than we ever imagined. In 1 Planck time, 10 to the negative 33 seconds, it expanded like 10 to the 57 times the scale factor, like something much bigger than we ever expected. So all the space got flattened out, basically. So if you have inflation, it's going to look pretty flat, is what I'm trying to say. But it also accelerates, so it's not quite flat. It's a little bit negatively curved, like a Pringle in a geometry. And if you drew a triangle on a Pringle, it would follow those same rules. I don't know if you could predict the shape ahead of time, because how do you go from one point to an infinite number of points and then have a shape all of a sudden? That breaks my brain to think about. Yeah.